NOAA's latest update shows the November sunspot number at 91.8, down significantly from the August high. This suggests that solar cycle 25 is indeed declining, that we are past the most dangerous phase and heading toward the relative safety of solar minimum. But this interpretation comes with significant caveats. Solar cycles do not follow neat, predictable curves. They are messy, variable, punctuated by bursts of activity that can occur at any phase. Some of the most powerful events on record have occurred during the declining phase of a cycle, when the overall activity level was dropping but individual active regions still had the capacity for extreme behavior. The Carrington event itself occurred in September of 1859, just a few months before the solar maximum of cycle 10. But the Quebec blackout of 1989 occurred in March, well into the declining phase of cycle 22. The timing of a major event within a cycle is less important than the characteristics of specific active regions. A single, magnetically complex sunspot can produce catastrophic flares regardless of where we are in the overall cycle progression. This brings us back to AR4294, the emergence of such a massive, magnetically complex sunspot during what should be the declining phase of solar cycle 25 is not unprecedented, but it is notable. It suggests that the Sun has not yet finished with the current period of elevated activity. Whatever the smoothed monthly statistics might indicate, the solar surface remains capable of producing events that could significantly impact Earth. The 11-year cycle itself is actually only half of a longer pattern. Each cycle, the Sun's magnetic polarity reverses. During cycle 24, the Sun's north magnetic pole was positive, and its south pole was negative. During cycle 25, these polarities have flipped. It takes 2 complete 11-year cycles for the Sun's magnetic field to return to its original configuration, making the true period of the solar magnetic cycle approximately 22 years. This 22-year pattern, called the Hale cycle, after the astronomer who discovered it, has been proposed as a factor in extreme space weather events. Some researchers have suggested that the most powerful solar storms tend to cluster at certain phases of the Hale cycle, perhaps when the orientation of the Sun's magnetic field relative to Earth is particularly favourable for energy coupling. The evidence for this hypothesis is mixed, but it represents one of many attempts to find predictable patterns in what often seems like chaotic solar behaviour. What we can say with confidence is that solar maximum represents a period of elevated risk. The number of active regions on the solar disk increases, the probability of M-class and X-class flares rises, the chance of Earth-directed coronal mass ejections goes up. During solar maximum, space weather forecasters issue more watches and warnings, satellite operators monitor their systems more closely, and power grid managers remain alert for signs of geomagnetic disturbance. The current situation exemplifies both the risks and the uncertainties of solar maximum. We have a massive sunspot complex facing Earth, one of the largest in a decade. We have already experienced multiple significant flares from this region and its neighbours. A coronal mass ejection is currently in transit, expected to produce G3 or possibly higher geomagnetic storming. All of this is occurring at a time when the Sun should be calming down according to statistical predictions. But here is the uncomfortable truth that solar physicists grapple with every day. We cannot predict when or whether a specific sunspot will erupt. We can assess probabilities, we can monitor magnetic complexity, we can track the evolution of active regions across the solar disk. What we cannot do is say with certainty that a particular region will or will not produce a major flare in the next hour, the next day, or the next week. The physics of magnetic reconnection involves instabilities that develop on timescales too fast, and at spatial scales too small for our instruments to track in real time. A sunspot can sit quietly for days, building magnetic stress, and then explode without warning. Conversely, a region that appears primed for eruption can rotate harmlessly off the solar limb without ever producing the expected event. The Sun keeps its own counsel, and our predictive capabilities, while vastly improved from even a decade ago, remain fundamentally limited. This is why the Watch and Warning System exists. NOAA's Space Weather Prediction Center monitors the Sun continuously, analyzing imagery from multiple spacecraft, tracking the evolution of active regions and issuing forecasts that attempt to quantify the probability of various space weather events. When they say there is a 15% chance of X-class flares, they are acknowledging both the potential for extreme events and the uncertainty inherent in predicting solar behavior. The cycle we cannot escape is not just the 11-year oscillation of sunspot numbers. It is the perpetual cycle of risk and uncertainty, of watching and waiting, of knowing that at any moment the Sun could produce an event that would test the limits of our technological resilience. We are currently in a period of elevated risk. The sunspot numbers may be declining from their August peak, but the massive active region on the Earth-facing disk demonstrates that the danger has not passed. Solar cycle 25 has exceeded expectations. It has produced more flares, more sunspots, and more intense activity than the expert panel predicted in 2019. Whether we have truly passed solar maximum, or whether there are more surprises in store, only time will tell. What we know for certain is that until this cycle reaches its minimum, likely sometime around 2030, we remain in a period when the Sun is capable of producing events that would challenge everything we have built. The cycle continues, the Sun breathes, and we watch and wait and hope that when the next great storm comes we will be ready. What Mars saw before we did. In the vast loneliness of the Martian surface, a robot named Perseverance continues its patient exploration of Jezero crater. The rover, which landed in February of 2021, is primarily tasked with searching for signs of ancient microbial life and collecting rock samples for eventual return to Earth. But like all NASA Mars missions, Perseverance carries instruments that monitor the space environment around it, tracking radiation levels and solar activity from a vantage point tens of millions of miles from Earth. Approximately 1 week before the sunspot, complex AR4294 rotated into view from Earth. Perseverance detected it from Mars. This detail, which might seem like a minor technical footnote, actually illuminates something profound about our ability to monitor solar threats. The Sun rotates on its axis once approximately every 27 days as seen from Earth. A sunspot that emerges on the far side of the Sun, invisible from our planet, will eventually rotate into view over the eastern limb. During the days or weeks when that active region is pointed away from Earth, we are essentially blind to its development. We cannot see it forming. We cannot track its magnetic evolution. We have no warning that a potentially dangerous structure is building on the solar surface until it swings around to face us. But Mars, depending on its orbital position, can sometimes see parts of the Sun that are hidden from Earth. When the geometry is favourable, spacecraft on or around Mars can provide advance warning of active regions before they rotate into our line of sight. This is exactly what happened with AR4294. The Perseverance rover, looking at the Sun from its position on Mars, detected the emerging sunspot complex days before Earth-based observers had any indication it was there. The implications are significant. If we had spacecraft stationed at multiple points around the Sun, observing it from different angles, we could maintain continuous surveillance of the entire solar surface. Active regions that currently take us by surprise after rotating onto the Earth-facing disk could be tracked from their earliest emergence. We could monitor their magnetic evolution, assess their flare potential, and issue warnings days or even weeks before the dangerous face of the Sun swings in our direction. This concept, sometimes called solar sentinels or a solar ring fence, has been proposed multiple times by space agencies and researchers. The idea is elegant in principle, but challenging in practice. Maintaining spacecraft at positions that provide useful viewing angles requires either heliocentric orbits interior to Earth, placing observers closer to the Sun than our planet, or gravitationally stable Lagrange points that allow continuous observation from fixed positions relative to the Sun. Both options involve significant mission costs and engineering challenges. Currently, our primary eyes on the Sun include the Solar Dynamics Observatory in geosynchronous orbit around Earth, the SOHO spacecraft at the L1 Lagrange point between Earth and Sun, and various instruments aboard NOAA's GOES satellites. These platforms provide excellent coverage of the Earth-facing solar disk, but limited visibility of regions that have not yet rotated into view. The fact that a rover on Mars, designed primarily for geology and astrobiology, was able to detect the current sunspot complex before Earth-based observers speaks to both the accidental benefits of our interplanetary presence and the gaps in our dedicated solar monitoring infrastructure. We have spacecraft scattered across the solar system for various scientific purposes. When their positions happen to provide useful solar observations, we benefit. But we have not systematically designed a network to ensure continuous all-angle coverage of the Sun. This matters because the worst-case scenario for space weather involves an event from an active region that we did not know existed until it was already pointed at us. Imagine a Carrington-class sunspot complex magnetically loaded and ready to erupt, rotating onto the Earth-facing disk with no prior warning. We would have at most a few days to assess the threat before the region reached optimal geo-effective position. If it erupted immediately upon coming into view, we might have less than a day of warning before the flare and CME were on their way. The Perseverance observation of AR4294 gave us a preview of what systematic early warning could look like. Solar physicists knew the region was coming. They had time to prepare observations, to alert space weather forecasters, to begin monitoring for signs of activity even as the structure was still rotating into view. This advance notice did not change the fundamental physics of the sunspot, but it improved our situational awareness and allowed for more careful tracking of the region's evolution. Amateur astronomer Patricio Leon, who has been following the current sunspot complex since its emergence, noted that it required more than 2 full days to rotate entirely past the eastern limb of the Sun. The sheer size of the structure meant that it was visible from Earth for an extended period during the rotation process. But even so, the earlier stages of its development, the initial emergence of magnetic flux from below the solar surface, occurred while the region was still hidden from our view. The Mars detection also highlights the growing capability of instruments designed for purposes other than solar monitoring to contribute valuable space weather data. Perseverance carries a radiation assessment detector that measures the energetic particle environment on the Martian surface, primarily to inform future human mission planning. But the same instrument that measures particles from distant cosmic ray sources can also detect the enhanced radiation that accompanies solar flares and CMEs. When the Sun erupts, Mars missions see the effects and can report them back to Earth. This distributed sensing capability has become increasingly important as our presence throughout the solar system has expanded. Spacecraft at Venus, Mercury, Mars, Jupiter, and beyond all carry instruments that can detect solar events. When a major eruption occurs, we can track the propagation of the CME through interplanetary space by observing its effects at multiple locations. This provides a kind of 3-dimensional view of solar storms that was impossible when our only sensors were based at Earth. The Parker Solar Probe, which is currently conducting the closest ever observations of the Sun, is scheduled to make its nearest approach in December of 2024, passing within just 6 million kilometers of the solar surface. This mission is providing unprecedented data about the solar corona and solar wind, information that will improve our understanding of how CMEs accelerate and propagate. The European Solar Orbiter mission, launched in 2020, is conducting observations from an orbit that takes it both close to the Sun and high above the ecliptic plane, providing views of the solar poles that have never before been possible. These missions are revolutionizing our understanding of solar physics, but they are scientific rather than operational assets. They were not designed to provide continuous real-time monitoring for space weather forecasting. The data they collect is invaluable for research, but often takes time to process and analyze. What we need for operational forecasting is something different, a network of spacecraft dedicated specifically to space weather surveillance, positioned strategically to provide continuous coverage of the entire solar surface and equipped with instruments optimized for real-time event detection and warning. The investment required would be substantial but not unprecedented. We already operate weather satellite constellations that provide continuous monitoring of Earth's atmosphere from multiple orbital positions. The same principle could be applied to solar monitoring, with spacecraft at the L1, L4 and L5 Lagrange points, plus additional assets in heliocentric orbits, providing all-angle coverage of the Sun at all times. Until such a network exists, we will continue to rely on fortuitous observations like the Perseverance detection of AR4294. We will continue to be surprised by active regions that emerge on the far side and rotate into view fully developed and potentially dangerous. We will continue to operate with less warning than we could have if we invested in the infrastructure that modern space weather forecasting requires. The sunspot that Mars saw before we did may or may not produce a catastrophic event, but the next one might, and the one after that. Somewhere out there on the far side of the Sun, the next great solar storm may already be building. We just cannot see it yet. The storm that almost was. On July 23, 2012, the Sun unleashed a monster. A coronal mass ejection of extraordinary power blasted away from the solar surface, accelerating to speeds exceeding 3,000 kilometers per second, carrying enough energy to rival the Carrington event itself. It was the kind of solar storm that space weather scientists had warned about for decades, the kind that could devastate power grids, disable satellites, and send modern civilization reeling. It missed Earth by approximately 9 days. 9 days in celestial terms is the difference between the rotation of the Sun carrying the eruption site away from the Earth direction and carrying it toward us. If the active region that produced this CME had erupted roughly 1 week earlier, when it was pointed at our planet rather than away from it, the consequences would have been severe. We would not be speculating about what might happen in a Carrington-level event. We would be recovering from one. The July 2012 event has become a touchstone in discussions of space weather risk. It demonstrates that the Sun remains capable of producing superstorms comparable to historical extremes. It shows that such events are not confined to the distant past, but can occur in the modern era, when our vulnerability to them has increased by orders of magnitude. And it serves as a sobering reminder that our safety from extreme space weather depends, to a significant degree, on luck. The CME originated from active region 11520, a magnetically complex sunspot group that had been producing flares for several days. The eruption that launched the massive cloud of plasma was associated with an X-class flare, though because the region was on the far side of the Sun relative to Earth at the time, our instruments could not directly measure its intensity. Analysis of the CME itself, using data from the stereo spacecraft that observed it from a favourable angle, suggested it was among the most powerful solar eruptions recorded in the space age. The transit time from Sun to Earth, had the CME been directed at us, would have been remarkably short. The initial speed measurements indicated the leading edge was travelling at approximately 2,500 kilometers per second. At that velocity, the plasma cloud would have reached Earth in roughly 17 to 18 hours, comparable to the transit time of the Carrington event CME. This rapid propagation was likely enabled by a previous CME that had occurred hours earlier, clearing the ambient solar wind out of the path, exactly the mechanism that scientists believe enhanced the speed of the 1859 event. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, published an analysis of the 2012 event that reached stark conclusions. He estimated the storm would have caused extensive damage to satellites, potentially disabling a large fraction of the GPS, communication, and weather monitoring constellations. The geomagnetically induced currents would have stressed power grids across multiple continents, likely causing transformer failures and widespread blackouts. The economic impact could have reached or exceeded $2 trillion. Recovery would have taken years. We dodged this bullet purely by chance. The sun does not aim. It does not care whether Earth is in the path of its eruptions. Active regions rotate across the solar disk, erupting when internal magnetic stresses reach critical thresholds, and the direction of those eruptions depends entirely on where the region happens to be pointed at the moment of the event. A region on the far side of the Sun produces a CME that races harmlessly into interplanetary space, posing no threat to Earth. The same region, a week earlier or later in its rotation, produces a CME that strikes our planet head-on. The July 2012 near miss was not unique. Throughout the history of solar observation, there have been numerous powerful eruptions that occurred when the Sun was pointed away from Earth. We know about them because our monitoring spacecraft can detect events regardless of their direction, and because some of those events were observed by spacecraft at other locations in the solar system. What we do not know is how many potential catastrophes we have narrowly avoided without ever realizing it. The statistics are sobering. Various estimates place the probability of a Carrington-class event within any given decade at somewhere between 1 and 12%. That range reflects genuine uncertainty about how often such extreme events occur and how we should define the threshold for Carrington-class magnitude. But even the lower estimates imply that over a multi-decade period, a severe event becomes quite likely. If the probability is 5% per decade, then over a 50-year span, the cumulative probability exceeds 20%. Over a century, it approaches 40%. These are not small numbers. We insure against risks with far lower probabilities. We build earthquake-resistant structures in seismic zones despite the uncertainty about when the next major quake will strike. We maintain fire departments even though any particular building is unlikely to catch fire on any particular day. The actuarial logic that governs prudent risk management suggests we should be investing heavily in space weather resilience. The fact that we are not suggests a collective failure to take the threat seriously. The 2012 event also highlighted the importance of the Stereo mission, a pair of spacecraft that orbit the Sun at roughly Earth's distance, but at positions ahead of and behind our planet in its orbit. These spacecraft can observe portions of the Sun that are hidden from Earth, exactly as Perseverance on Mars observed AR4294 before it rotated into our view. When the July 2012 CME erupted, Stereo A was positioned to observe it in profile, capturing the expansion and propagation of the plasma cloud as it raced outward through the solar system. Without Stereo, we might not have known the full magnitude of what we dodged. The event would have been recorded as a far-side eruption of some undetermined size, one among many such events that occur during solar maximum. Instead, we have detailed measurements of its speed, its mass, its magnetic configuration, all the parameters needed to assess what it would have done had it been aimed at Earth. The data paint a picture of a storm that would have rivaled or exceeded the Carrington event in intensity. The speed was comparable. The magnetic structure was complex and energetic. The quantity of material ejected was enormous. All the ingredients for catastrophe were present. Only the geometry was wrong. Wrong from the Sun's perspective in terms of hitting its target, but fortunate from our perspective in terms of avoiding disaster. Since 2012, the space weather community has worked to ensure that this near miss is not forgotten. The event is cited in reports, referenced in policy discussions, and used as a case study in training exercises. When agencies conduct tabletop simulations of severe space weather events, the 2012 eruption provides a realistic template for what a modern Carrington-class storm would look like. But memories fade. institutional attention shifts to more immediate concerns. The officials who were alarmed by the 2012 analysis have retired or moved on. New decision-makers, unaware of how close we came, allocate budgets based on threats that feel more tangible and immediate. The blind spot that allows us to ignore space weather risk regenerates itself with each passing year of quiet sun. The current sunspot complex facing Earth is a reminder that the threat has not gone away. The CME currently in transit is a smaller scale demonstration of the processes that could, under different circumstances, produce a civilization-altering event. We are playing a game of celestial roulette, spinning the cylinder each time an active region faces Earth, hoping that the chamber is empty. In July 2012, we got lucky. The chamber was empty. The bullet passed harmlessly by, but the gun is still loaded and the sun keeps pulling the trigger. Sooner or later, our luck will run out. The question is not whether we will face another Carrington-class event. The question is whether we will be prepared when it comes. Watching the sleeping giant. As this documentary reaches you, the sunspot complex that has commanded our attention for the past week continues its slow rotation across the Earth-facing disk of the Sun. AR4294, along with its magnetically intertwined companions, AR4296 and AR4298, remains one of the most impressive solar features observed in the past decade. Its dark cores, each one capable of swallowing Earth, continue to churn with magnetic energy. Its beta-gamma-delta classification has not changed. The potential for a major eruption has not diminished, and yet, for the past several days, the region has been remarkably quiet. This is the paradox that haunts space weather forecasters. The largest, most magnetically complex sunspots do not always produce the largest flares. Sometimes they sit peacefully for days, building stress without release, before rotating off the western limb and disappearing from view. Other times, they explode repeatedly, hurling energy and plasma into space with each successive eruption. There is no reliable way to predict which behavior a given region will exhibit. The current forecast from NOAA's Space Weather Prediction Center reflects this uncertainty. M-class flares are considered likely, X-class flares are possible. Beyond these probabilistic statements, we cannot say much with confidence. The Sun keeps its own schedule. What we can say is that the threat we have discussed throughout this documentary is not hypothetical. The Carrington event happened. The Quebec blackout happened. The 2012 near miss happened. Miyake events have left their signatures in trees around the world, evidence of storms far exceeding anything in recorded human history. The Sun is capable of producing events that would fundamentally alter the functioning of modern civilization, and we have done remarkably little to prepare for that possibility. The CME launched by the M8.1 flare on December 6th is expected to arrive at Earth within hours of this recording. NOAA has issued a G3 strong geomagnetic storm watch, indicating that significant auroral activity is likely and some infrastructure impacts are possible. This event will almost certainly not be catastrophic. It will produce beautiful displays in the northern sky for observers at high latitudes. It will cause minor fluctuations in power grids and brief disruptions to high-frequency radio communications. Satellite operators will monitor their systems closely and implement protective measures as needed. Life will go on. But each such event is a reminder that we orbit a star capable of great violence, a reminder that the infrastructure we depend on was built without serious consideration of space weather hazards, a reminder that our continued safety depends on a combination of physics we cannot control and preparations we have largely failed to make. The sunspot complex will continue rotating toward the western limb over the coming days. It may erupt before it disappears from view, or it may slip quietly around to the far side of the Sun, building energy for a future display. If it erupts while still facing Earth, we will have minutes of warning for the radiation effects and hours to days of warning for any associated CME. That timeline is sufficient for operational responses shutting down satellites, reducing power flows, alerting authorities, but insufficient for the kind of fundamental preparations that would make a real difference. The broader lesson of this moment is that we live in a narrow window of technological vulnerability. 200 years ago, a Carrington-class event would have been a spectacular light show and nothing more. The auroras would have dazzled observers, telegraph wires would have sparked and smoked, but the basic functioning of society would have continued uninterrupted because society did not yet depend on electrical technology. 200 years from now, if we are thoughtful about how we develop, we might have power grids hardened against geomagnetic storms, satellite constellations designed with redundancy and rapid replacement capability, and early warning systems that provide days or weeks of notice before a major event arrives. The vulnerability we currently face is a consequence of our particular moment in technological history, advanced enough to depend on fragile systems, but not yet advanced enough to protect them. The question is whether we will use the time we have to close that gap. Every year without a major event is an opportunity to invest in resilience, to harden critical infrastructure, to develop the monitoring capabilities that would give us maximum warning of incoming threats. Every year without a major event is also an invitation to complacency, to assume that because nothing bad happened yesterday, nothing bad will happen tomorrow. We know the sun is capable of producing extreme events. We know our infrastructure is vulnerable. We know the economic and human costs of a Carrington-level storm would be staggering. What we do not know is when the next such storm will occur. It could be decades away. It could be next week. The only honest answer is that we cannot predict it with any precision. What we can do is prepare. We can invest in transformer protection. We can develop strategic reserves of critical components. We can expand our solar monitoring network to provide early warning of threats developing on the far side of the sun. We can conduct the research needed to better understand and predict extreme space weather events. We can take the threat seriously rather than relegating it to the category of exotic risks that we prefer to ignore. The sleeping giant on the face of the sun may wake at any moment, or it may slumber peacefully until it rotates out of view. Either way, it will return. The sun rotates once every 27 days, bringing active regions back into Earth's line of sight on a regular schedule. And even if AR4294 fades into obscurity, other active regions will emerge. Solar cycle 25 is not yet over. Solar cycle 26 will follow. The sun will continue its 11-year rhythm of activity and quiet for as long as the hydrogen fuel in its core holds out, which is to say for the next 5 billion years. We are visitors in this solar system, brief flickerings of consciousness on a small planet orbiting an average star. Our civilization, for all its complexity and sophistication, has existed for only the blink of a cosmic eye. The sun was here long before us and will remain long after we are gone. Its processes operate on timescales that dwarf human history. Its eruptions release energies that dwarf anything our technology can produce. And yet, here we are, watching, measuring, trying to understand, trying to predict, trying to protect ourselves from forces that do not know we exist and would not care if they did. The monitors will continue tracking AR4294 until it disappears over the western limb. The forecasters will continue issuing their probabilistic assessments. The satellite operators and grid managers will continue their vigilant watch. And somewhere out there, below the visible surface of the sun, magnetic flux tubes are rising through the convection zone, building the active regions of tomorrow. Some of those future regions will be small and inconsequential. Others will be giants, comparable to or exceeding the monster currently facing Earth. Eventually, inevitably, one of them will erupt at the precise moment when it is pointed directly at our planet. When that happens, we will learn how well we have prepared. We will learn whether our infrastructure can withstand the assault. We will learn whether our civilization is resilient or fragile. Until then, we watch, we wait. We hope that when the sleeping giant finally wakes, we will be ready. Thank you for joining me on this journey through the science and mystery of solar storms. I hope you found it illuminating, perhaps a little unsettling, and ultimately thought-provoking. If you enjoyed this exploration, please remember to like and subscribe so you never miss our future documentaries. Share your thoughts in the comments below. Tell me what aspects of space weather you would like to explore further. Tell me about the auroras you have seen or hope to see. Tell me how you think we should prepare for the inevitable day when the sun reminds us who is really in charge. Please remember that this documentary represents a synthesis of current scientific understanding combined with informed speculation about future possibilities. It is intended to educate and engage rather than to frighten. The probability of a catastrophic solar event on any given day is low. The probability of such an event within our lifetimes is higher but still uncertain. What is certain is that preparation is wiser than denial, and that understanding is the foundation of resilience. The sun will rise tomorrow, as it always does. Its light will warm our faces, its energy will power our world, and somewhere beneath its seemingly placid surface, the forces that could reshape our civilization will continue their slow, patient accumulation. Sleep well tonight, dream of auroras dancing across northern skies, and know that out there, 93 million miles away, the sleeping giant breathes. Good night.